Now what I've set out to do is essentially prove Green's theorem for a small rectangle, at least in the limit as the rectangle gets small, based on the values of the m, the n, and their derivatives at a sample point. So once I've been able to prove, assuming I am, because I'm running into a problem with uniform continuity. Okay, it turns out I need uniform continuity over a larger region. I don't need it on this small region, but I think I might need it on the larger region. And we'll talk more about what uniform continuity is and develop that idea if we're inclined to do so. Okay, so let's assume that I am able to prove it on any small rectangle I want to prove it on. Okay, now this is a small rectangle, and we have a simple closed curve over which we want to prove Green's theorem. Okay, this is a rectangle, it's not a curve, but if the rectangle can be made as small as we wish, we can make a lot of really small rectangles. So what I'm going to do should work. Now let me just show what happens if I construct another rectangle above this one and do the integral with a positively oriented curve. In a positively oriented curve, basically you can say that if you go around the curve with your fingers using the right-hand rule, the your thumb, the cross product or the loop, is in the positive sense. In other words, if you have x, y, and z on a right-handed coordinate system, your right hand gives you your thumb pointing in the direction of the z-axis, okay? And another way of looking at it is if you walk around this curve, the interior is always on your left. It's a positively oriented curve. Okay, so I do another rectangle that shares this one side, one edge of the original rectangle. I go around it in a positive sense. Well, whatever my integral along this path is, in the first rectangle, the path from here to here, is going to be equal and opposite to the integral along the path from here to here. So that these two cancel each other out. So I can just erase this part, and I'll go ahead and do that. It's going to be smudged, but compared to other flaws that we've seen here, it's no big deal. Okay, so now I can extend the theorem here. Okay, and then I can extend it to another rectangle down here. And still another one over here. And we got any colors left? Yet another one over here. So now my first rectangle is gone. And of course, each of these rectangles has its own sample point. Just anywhere in the rectangle, as long as I have continuity. And I'm assuming I have continuity on every one of these rectangles, okay? And assuming that continuity is sufficient on any individual rectangle. Okay, well, it's clear that I can continue and essentially then take the region and split it up into rectangles, although not perfectly. can come along here, here, and here, and here. And maybe I can even get a little bit of it in here. Okay. Now, if I can do that, same thing on all these rectangles, it doesn't take much to see that everything, every complete rectangle cancels out every rectangle that surrounds it. And what I'm going to be left with is just these regions that aren't complete rectangles. All the way around. I'm going to need this one and this one and one here. So forth, all the way around the boundary. Only the pieces of rectangle that coincide with the boundary are going to end up not being canceled by the rectangles that surround it. And it looks like I'm going to have to use this one. Of course, this side cancels with this one, this cancels with this one, this doesn't cancel with anything. Okay? But in any case, you end up with these rectangles that are not quite rectangles, they're truncated by the boundary. Okay? So you essentially eliminate any effects of whatever happens inside of here. And I'm not going to try to be too neat about this. But any edge of any rectangle that coincides with another edge will be lost. Okay, well, I'm not going to try to neat it up. That's the idea. And the reason I'm worried about uniform continuity on this region, which is not an assumption of Green's theorem, and I'll hasten to add that Green's theorem works. You can do the facile proof you see in your textbook that proves that you don't need uniform continuity, which means that if I actually do need uniform continuity, then I can't develop the proof that I was trying to develop. I can develop it, but it's not going to work. It's not going to be consistent. Foundationally, at the very foundations of mathematics, something's going to get screwed up. With that proof. The proof just doesn't work. Now, I still think it does. I still think I can make it work. Okay, so now what I think is, since this is a closed region, if we include the boundary, I'm pretty sure we include the boundary with the region, although I don't see that stated in the textbook. But if the region includes its boundary, then we have a compact set, and continuity implies uniform continuity, and that's kind of what it comes down to. But since you don't know the topological and analytical, you haven't been through those ideas and done a lot of proofs of that nature, I've got to develop these things, okay, in a way that can be understood by an extraordinarily bright multivariable calculus student. So that's where we are.